We're going to pick up chapter 7 where we left off last week. And we're going to share the slides first. Eventually. Try that again. There we go. Sometimes you have to click it twice. There we go. That's where we paused. Let's see if we back up one. Yeah, we finished off last week with Dalton's law of partial pressures. So we've covered all the gas laws. And next week we're going to do a lab using one of those laws. The first one, actually, Boyle's law. Okay. Just as a quiz, what's Boyle's law relating? Remember when you have gases, if you know pressure, volume, temperature, and moles, you can completely describe gas behavior. All right, so which one of these which one of these are going to be two of the variables in Boyle's law? Remember? No? Pressure, volume. That means these two have to be held constant. Okay? All right. So be sure and read the lab before you come to class next week. I would really appreciate it. All right. So now we're going to pick it up with changes of state. Right. We have an intuition about the change of a state. It's a physical change. In other words, the identity of the substance does not change. It's not altered in this process. Okay. Who just came in? And you are? I'm sorry? Abby. All I had is the last name. Okay. That helps a lot. So in this physical change, you can either, for our purposes, we're going to stick to gases, liquids, and solids. So you're making a transition from a gas to a liquid to a solid or the other direction. And let me look ahead just a couple of slides. Okay. This change of state is usually accomplished by either heating or cooling. You add energy to the system or you remove energy from the system, and eventually you'll get a change of state. And there are various names assigned to the different changes: freezing, condensation. I'm going to show you draw you a thing that's on the next slide. How to keep these things straight. What's what? Deposition, melting, evaporation, sublimation. So rather than go to the next slide, let's just say, well, maybe I better. Because this one this one doesn't put them the same way I would. I'm going to put gas up here on top. And I'm going to put a liquid over here. And a solid over here. Okay, so we've got these three states, and this is the same substance. All right, if it were, I don't know, gold, you could melt gold. Actually, you can evaporate gold if you get it hot enough. But these are the phases. I don't like that marker. Try it differently. Now, the process of change from one to the other can go forwards or backwards. You can go from a liquid to a gas. Like that. That would be evaporation. What if you went from a gas to a liquid? That's condensation. Okay. What if you went from a liquid to a solid? Let's see. I'm on the outside going that direction. Like this. So if I went from a liquid to a solid, that would be, what are they calling it? There are various names you can use. Freezing. Will be consistent with the authors. And solid to liquid is melting. Okay. Those are fairly common, and we know what they are. If you take water, for instance, pull it out of the freezer, and it starts off as a solid, and heat it up, or eventually just leave it out, and it'll melt. And if you heat it further on the stove, you can evaporate it, make a gas out of it. What about going from solid to gas or gas to solid? You can do that with water. You need some special equipment. They call it freeze drying, or the fancy name is lyophilizing. But one more common that you may run across is dry ice, solid carbon dioxide. If you set it out on the bench, it'll go straight from a solid to a gas, and you can't see the carbon dioxide, but you can see its effect on the humidity in the air. You'll see the cloud forming around it. And that going from, let's see, I'm going this direction on the inner circle. This direction from a solid to a gas, that's called sublimation. Right? Going the other direction, if you go from a gas to a solid, is called deposition. Spell that right? Yeah. The other, since we're talking about how do you go from one to the other, you either add heat or you subtract heat, we're going to use terms. They're not using terms like that here. I think it makes a difference. Yeah. Have we defined these terms yet? Exothermic and endothermic? I don't think we have. Okay. Exothermic. And endothermic. They're talking about heat transfer. But I find it useful to think of heat transfer in terms of system and surroundings. If you have a system, and it could be defined for you, or you could define it, whatever it happens to be. We could say the system is an ice cube, and then the surroundings is everything else. Okay, if heat is being added to the system, right, and we give that a small q for heat. If heat is being added to the system, we also give it a plus sign, and that's endothermic. Heat is going into, endo means into, heat's going into the system. So when heat goes into the system, if it's an ice cube, what is it going to do? It's going to melt, right? So melting is an endothermic process. Okay, that means the opposite direction, like freezing, would be an exothermic process, which means heat is leaving the system. In that case, Q is a negative. Everything, all the signs on these, you can put values to these. So many joules per mole, joules per gram. You can put values on these, and if there's a value associated with it, it would have to be positive if it's endothermic and negative if it's exothermic. So this one is going to be exothermic. Freezing. Okay, your diagram there, that slide, puts it in terms of heat absorbed, heat released. All right, so heat released is exothermic, heat absorbed is endothermic. All right, how about the others? If you go from, say, a liquid to a gas, you have to put heat into it, don't you? Yeah, you got to add heat. So this is endothermic. Okay, that means condensation would be exothermic. Okay, how about the other one, the last one? It looks like if I'm going the same direction all the way around, the outer one should be endothermic. If we go from a gas to a solid, but it's not. If we go from a gas to a solid, it's got to give up heat. Think of it in terms of, we have talked about the kinetic molecular theory. That's what we started off with. I remember that. Think about the molecules. What are they doing? Right? If it's a gas, they're moving really fast and they're far apart. If it's a solid or a liquid, they're getting closer together and they're slowing down. That means they have to give up energy. So when we go to deposition, when we go from a gas to a solid, we have to give up energy. This would be exothermic. And the other direction would be endothermic. Okay. Any questions about that? Aside from the fact that it's kind of messy. It's helpful to think in those terms, in terms of a system and what are the molecules doing. All right. Oh, I should have looked ahead. So here we have slides that are telling us, let's see if we got it right. Let's see, melting, endothermic. Yep. Sublimation, endothermic. Evaporation, endothermic. We're good there. Heat is absorbed into the system. Exothermic, freezing. Yep. Condensation. Here, exothermic. And deposition, exothermic. Okay, got them all right. Heat is being given up in order to change state in the other direction, gas to solid or liquid to solid. Or liquid to gas. Where are we on? Exothermic. We're going this one. All right. What's the difference between endothermic and exothermic change? Well, I always look at the words. If the words are chosen correctly when we name things, then we should be able to tell from the name what we're talking about. Right? Into, heat. Heat's going into the system. Exo, leaving. Heat's leaving the system. All right. This evaporation of liquids, in terms of the molecules involved, or atoms for that matter, because we can evaporate atomic liquids. Let's see, how about mercury? Mercury is a liquid. You think mercury can evaporate? Oh, yeah. In fact, if you break a when we used to have mercury thermometers, if you broke a mercury thermometer on any kind of surface, it could be carpet, it could be, well, it's unlikely on carpet, hard surface like tile or linoleum, then that mercury will get down in the cracks. And over time, it will evaporate. And if your home is not well ventilated, it'll build up mercury in the atmosphere and you'll breathe it in and problems. Right? Mercury is a powerful neurotoxin. Messes with your nerves. In fact, there's one form of mercury, an organic form, dimethyl mercury, that is extremely hazardous. I mean, if you even think you're in the vicinity, run the other way. There was a scientist, a woman, years ago. several decades, who was working with dimethylmercury in environmental research. And she was very careful. Right? She wore her protective clothing, her masking. She even double gloved. And I think they were using latex back then. And she didn't know it at the time, but she got a drop of that on one of her gloves, that dimethylmercury. Well, that stuff is organic. It goes right through organic molecules. And latex is an organic molecule. So it went straight through. She didn't realize it until a couple of weeks later when she started to show symptoms of neurotoxicity. It took 3 or 4 more weeks, but eventually it killed her. So that's my scary story for today. Let's celebrate Halloween. So for liquids to evaporate, we have to add enough energy to them. Right? Endothermic. We have to add enough energy to break any attractive forces that are holding those molecules together. Right. Remember, one of the postulates of the kinetic molecular theory was that the molecules, the atoms in the gas or the substance, act like billiard balls. Right? They don't attract, they don't repel one another. Well, in fact, they do. One or the other. And now we have to incorporate that modification, because when you subtract enough energy, well, this is endothermic. When you add enough energy to the liquid and you introduce more kinetic energy to those molecules, then the attractive forces become less effective. Right? They smack each other with higher energies. They're together a shorter period of time, and the energy of impact overcomes any attraction that they may have for one another. When that happens, then they can change phase from liquid to gas. The same thing would happen for solid to gas in carbon dioxide, solid carbon dioxide, dry ice, right? Heat from the environment or from the desk. If you just set a piece of it on the desk or on the floor, heat is transferred in to the substance. Let's see, here it is, sublimation. And it's enough heat to break any attractive forces between the carbon dioxide molecules. You can go the other direction too. If you extract heat from a substance, if you exothermic process, then you decrease their kinetic energy. Now they're striking each other with less force, and any attractive forces becomes more significant. As a percentage of all the forces involved, the attractive forces eventually are strong enough to hold those things together in the liquid phase. All right? So that's where we're going with all this. When we often refer to the liquid phase, when it changes to a gas, we call it the vapor phase for that liquid. They're synonymous. The vapor phase is the gaseous phase of a liquid. Now, the transition from liquid to gas is sensitive to both temperature and pressure. So you add more energy to it, or you can decrease the head pressure, and you get more of the liquid molecules being removed into the gas phase. Well, you can do that with solids too. Right? That's where we get the freeze drying effect. If you decrease the pressure in the freeze dryer to, let's see, we used to use in the neighborhood of 10 millibar or less. It's pretty low. Not a perfect vacuum, but low enough. And we'd have frozen product, we'd stick in the lyophilizer, shut the door, and turn on the vacuum. Then we'd apply just a little bit of heat to it, not much, because they're sitting on metal trays that are heated. And that would be just enough energy to start subliming solid water, ice, into gas. And of course, the vacuum's running continuously, it just sucks off that gas as it comes out. But the evaporation would take place whether we had low pressure or high pressure. It's just the rate of evaporation increases when you decrease the head pressure. Now, let me remind myself, are we going to talk about that? Or should I interject that now? No, we are going to get to that. Okay, good. So that's enough for now. Okay. Oops, I gave you the answer already. Is heat absorbed or released during the evaporation of a liquid? Okay. If we got to go from liquid to gas, you got to add energy. So it's added energy. It's endothermic. All right. Oh, okay, now we're going to talk about the evaporation of a liquid in a closed container so that we can get a handle on the effect of this head pressure. All right. So if we have a closed container and they're using a Erlenmeyer flask there, that's okay. Like this, like that, flat like that. And if we put a stopper in it, and we have a liquid down here, okay? As soon as we put that liquid in there and stopper it, there's a process by which molecules from the liquid are escaping into the headspace above. They're going like that. That's initial. When we first start out, that's the only process that happens. Why? Because there are none of them up here. So it's going to evaporate. And if it evaporates fast enough, you can actually measure a temperature change. All right. So what happens when we start getting a significant number of those molecules in the headspace, in the gas phase? We got a liquid and a gas phase here. Well, eventually, these molecules are impacting the surface of the liquid, and some of them stay there. They feel the tug of the liquid, and they stay in the liquid phase. So eventually what you get is an equilibrium in which the rate of evaporation equals the rate of condensation. Okay, at that equilibrium, and that's what the far right jar is showing you. At that equilibrium, what we see in the flask is the volume of the liquid doesn't change anymore. And this only happens when you have it stoppered. Right? If you leave the stopper off, eventually it'll all evaporate because it's eventually evaporating into an infinite space. But if we keep the stopper in there, then we establish an equilibrium between the two. And it happens at different rates for different materials. It depends on the attractive forces between them. If you use water, right? Remember when we drew water like that? And it has a dipole like this, and it has a negative side here and a positive side here. So those molecules attract one another. Right? This negative side on one molecule is attracted to the positive side on the other molecule. And that's a strong attraction. But if you have something like, I don't know, diethyl ether, yeah, let's make it dimethyl ether. It's easier to draw. That's a nonpolar molecule. Right? You may have polarity going this way and this way, but they cancel each other out. So the molecule is nonpolar. So you don't have those positive negative interactions that hold together. This one evaporates really quickly. Right? If you've ever smelled ether, then you won't forget it. It's very distinctive odor. It's also hazardous for other reasons. So these liquid molecules are escaping into the vapor phase, and the vapor is being condensed into the liquid phase at the same rate when we reach equilibrium. And that's what's being represented by that far right. So how do we characterize this equilibrium? Well, For this course, we're not gonna talk about those equilibrium calculations that you can do. It's just suffice it to say that it's established, and you can see it macroscopically. You can see the change. Actually, in the beginning, you can see the level of the liquid drop. And when equilibrium is established, it stops decreasing. The volume of your liquid doesn't change anymore. What you do establish, though, for any of the liquids, whether it's water or diethyl ether or any other compound like ethanol, maybe, the drinking kind, it will establish a characteristic pressure, what we call a head pressure in that space above there. And it's dependent on two things. What's the molecule and what's the temperature? So if we know it's water, then we can say, all right, we know that at this temperature, it's going to be that pressure. If we change it to this one, then we use a different chart at a certain, if that's same temperature, then it's going to be a different head pressure for this one. In fact, it's going to be much, much higher because it evaporates more easily and puts more of these molecules in the headspace. All right. That's known as the vapor pressure. And there it is in black and white. The magnitude of the vapor pressure depends on the nature of the molecule and the temperature. You would have an extremely, almost catastrophic head pressure if you were using liquid helium. Liquid helium, it's only liquid at, let's see, helium, the liquid, is at 4 degrees. Now, excuse me, just 4K. Right? It's almost absolute zero. That's probably the coldest thing we can create in bulk is liquid helium. And in fact, for the longest time, these magnetic resonance imaging machines that the hospitals used, actually, they were used in research first. They had to cool the magnets with liquid helium because superconductivity, we couldn't establish it at higher temperatures than that. And then we developed materials that would be superconductive at higher temperatures. So then we could use liquid nitrogen, which is what they typically use now to cool the magnets. So the attractive forces of the helium atoms for one another is extremely low. Right? So you get a monstrous head pressure. In fact, if you're going to do this experiment, you need more than an Erlenmeyer flask. You need a stainless steel vessel to hold the pressure. In fact, helium's strange. Liquid helium is very strange. I've seen it up close and personal. You know what a dewar is? DEWAR. Think thermos bottle. Right? It's 2 layers with a vacuum in between, and both layers are silvered on the not on the inside but the outside. And what it does is it insulates the material from the surrounding environment, so it doesn't evaporate so quickly. So I've seen a dewar like this. There's a vacuum in here, and then you have liquid helium here. The cohesive forces of helium with the walls of the container are much stronger than the cohesive forces of helium for itself. The adhesive forces, I should say, helium and the walls of the container are very strong, as opposed to the weak forces of helium with helium. So what it tends to do is the liquid walks up the walls and walks its way right out onto the floor. Strangest thing I ever saw. Okay. We often refer to those substances that have a relatively high vapor pressure at, say, room temperature, would be typical, are considered volatile substances. In fact, the OSHA, I know what OSHA is, Occupational Safety and Health Administration, and the EPA have standards for various commercial products. And you'll see it on the side of the container. They'll say, what's the percent of VOCs? VOC is volatile organic compounds. So they try to reduce the presence of those volatile organic compounds because as they're curing, like a paint, you put a paint on your wall, and you can smell some of the odors. Some of those are volatile organic compounds. Most of them, though, are just breakdown products of the paint in storage. But it used to be that paints were dissolved in organic compounds, right? And there was some advantage to that. They would dry really quickly because organic compounds typically are more volatile than water. But they're called volatile for a reason, because they have high vapor pressure at room temperature. Okay, let's see. A liquid in a closed container evaporates for a short time, then condenses as the number of vapor molecules increase. The process is known as, then condenses, okay, it's equilibrium. Yeah, it's an equilibrium because they're describing two processes, evaporation and condensation, both. Right? So the process is a physical equilibrium. Now we can speak in terms of chemical equilibrium too, but I don't think we're going to cover that in this class. I'm pretty sure we don't. We may talk about it a little bit in chapter 9, chemical reactions, but we're not going to be as rigorous with it as I am with my general chemistry class. All right, boiling. All right, let's see. Boiling is evaporation. Is evaporation at ambient pressure. Right? So like we mentioned earlier, the liquid can convert to a gas simply by evaporating, and you don't see what we typically refer to as boiling. You don't see bubbles forming inside the liquid. This is all a surface process for evaporation. Boiling happens when the temperature of the liquid produces a vapor pressure that exceeds the vapor pressure over it. So if you have an open container, say let's keep it simple. You got water in this container and you're heating it on your stove. Right? It will boil when the vapor pressure of the liquid, when the temperature raises the vapor pressure of the liquid. Remember, vapor pressure is sensitive to temperature. When the vapor pressure at the surface of the liquid is equal to and slightly above the vapor pressure bearing down on it. So if it's an open container and you're at sea level, it'd be 1 atmosphere. If you're here, it's a slightly less pressure, not much, but slightly less. If you're in Beckley, where I live, you're half-mile high. So you're going to see the vapor pressure, the boiling point will decrease because you don't have to put as much heat into it to exceed, it's for the vapor pressure to exceed the atmospheric pressure above it. That's why when you go to, say, Denver at a mile high, your 3-minute egg might take 4.5 minutes to boil because you can't get the water hot enough. It boils at a lower temperature. And if you go to the top of Mount Everest, I think it boils at maybe, I don't know, 78 degrees Celsius instead of 100. So it would take you forever to boil your lentils at the top of Mount Everest, probably more time than you have up there, or you need to get down. Right? They say, what do you go to the top of Mount Everest? It takes you hours to get there. You can stay there for maybe 10 or 15 minutes, and then you have to start the trek back down before it gets dark or a storm moves in. That's not my idea of fun. Okay. So this process occurs when the vapor pressure of the liquid reaches the value equal to that of the external pressure over the head. That's why pressure cookers are used when you want a higher temperature of your inside the cooker than you can generate with an open container, right? We artificially increase the pressure against the liquid that's in your pressure cooker, so it only boils at a higher temperature. And they typically have three pressures that you can have: 5, 10, or 15 psi in excess. And you have these little weighted things that sit on top. And when it starts going, you've reached that pressure. We use it for canning. Right? If you have anybody here can? Okay, so you know what I'm talking about. When you stick those jars in your pressure cooker and you run them for 15 or 20 minutes, whatever, then you have to let it cool down before you can extract them. What it's doing is it's increasing the temperature in there above that which the microorganisms can survive. It's much more effective at killing microbes than just boiling them on the surface of the stove. Okay, so there's an example of something that's boiling. I don't know what it is. Colored water, maybe. So when we identify the boiling point, that's the temperature at which this substance will go from liquid to gas, and the vapor pressure exceeds the atmospheric pressure above it. And that boiling point can change depending on the external pressure. Now, I just described it for you. The higher you go, the lower the temperature required to boil the liquid. So if you are in outer space and your faceplate blows out, right? I think actually what's going to happen is you won't boil. It happens so quickly that you'll actually freeze solid. Anyway, the normal boiling point is referencing the standard temperature and pressure. Well, actually, the temperature is dependent upon the substance, and the pressure is 1 atmosphere. So if we establish the normal boiling point at 1 atmosphere pressure, whereas the boiling point can be any pressure. I think that's to standardize measurements. Right? If you're comparing several different substances, if you know the pressure is the same on them, then the boiling point is easier to compare and make judgments about what's happening inside the liquid on a molecular level. Okay, all of this change in boiling point is due to the pressure on the surface of the liquid. If there's more pressure, you have less evaporation. So in order to get it to boil, you've got to add more energy to it. It's fighting against that external pressure. All right, let's see if I was kind of off. The top of Mount Everest, 70-degree boiling point for water. Mount McKinley, well, they don't call it Mount McKinley in Alaska anymore, do they? Remember, you know what it's called now? Denali. That's an Eskimo word. I don't remember what it means, but they don't call it McKinley anymore. Let's see. There's a good one, Death Valley, which is below sea level. So the pressure in Death Valley is higher, right? It's about, well, it looks like 10 millimeters of mercury. Not much, but it's measurable. And the boiling point of water now is about a half a degree higher. It'd probably be even more than that if you were at, let's see, what's lower than Death Valley? The Dead Sea. I think the Dead Sea is almost 1,000, is maybe 500 or 600 feet below sea level. Okay. The boiling point of a liquid is defined as the temperature at which vapor pressure of a liquid is equal to the atmospheric pressure exerted on the liquid. It's that simple. Okay, what's the vapor pressure of water at 100 degrees if boiling? Vapor pressure is 1 atmosphere. If it's boiling at 100 degrees, the external pressure and the vapor pressure of the liquid have to be balanced, and that's 1 atmosphere, 100 degrees. So let's see. We measured the boiling point of water here in one of our earlier labs, didn't we? Boiling point, freezing point, right? Did anybody get 100 degrees? Should have been a little bit less than 100. Yep. And there it is in green lettering. Is anybody in here colorblind? The reason I ask that is we've been encouraged when we create these slides, when we modify Brightspace courses, certain colors we shouldn't use because they don't work well for colorblind people. And I think green is one of them. I mean, if you're I don't know if this is a proper term, profoundly colorblind, profoundly deaf, I understand. Profoundly colorblind is you really have a problem with colors, right? I have a slight problem, like when I'm sitting at a stoplight, it doesn't turn green for me; it turns blue, slightly blue-green. And I don't know if that's the light or it's me, but I think I have a little bit of color blindness, not much. It's more prominent in men than it is in women. It's what they call it, sex influenced, not sex linked. Okay. So we've started talking about this already, the intermolecular forces in liquids. Intramolecular forces, there's a difference. Let me put it over here. You got to look at the word intramolecular versus intermolecular. Now, they still use terms in high school sports, intramural and intermural. They don't. They used to when I was in school. Intramural sports was your A team is scrimmaging against your B team, right? It's inside the school bounds. Intermolecular or intermural is this school is battling this school on the field. Okay. So if we take that and use it in chemical terms, the intramolecular forces are those forces that hold molecules together, the bonds that hold the atoms together. Whereas the intermolecular forces are those that can attract molecules toward one another. Right? So I think that's what this is going to say. Forces within molecules, yes, intra. Versus inter, those are forces between molecules. All right, now let's see. I have a nasty habit of stealing my own thunder. If I look ahead, maybe a couple of slides, I'll be sure of it. Okay. Let me go to the next slide. So the intermolecular forces are those that attract molecules to one another. Sometimes they're very weak, sometimes they're extremely strong. Right? On a scale, the intermolecular forces between water molecules are very, very strong. That's why water is a liquid at ambient temperature, room temperature, and 1 atmosphere pressure. If you didn't have those forces, water would typically be a gas. Right? And then we'd all be in real big trouble because there wouldn't be any liquid water on the surface of the earth. Okay. Now, how about the strength of the forces? if these are within molecules holding the atoms together, and these are between molecules holding molecules together, which one should be stronger? You can take a wild guess if you want. Let's see. Yeah. Which ones? Within should be stronger. Yeah. I mean, look at it this way. What if it were the other way around? What if the forces between molecules were stronger than the ones within molecules? You're close. The molecules would get ripped apart because the strength of the forces between molecules would be too strong for the structure of the molecule and just pull it apart. So it has to be this way. Within intramolecular forces must be stronger than intermolecular for practical purposes, for practical reasons. Otherwise, we don't have any molecules. As soon as you make a molecule, it gets ripped apart. It's just that simple. Okay, we can characterize these forces. I'm going to erase this now. We can characterize these forces and name them. We categorize them. Let's say we're going to categorize them based upon the strength of the force, okay, and how the force is made. Dipole-dipole interactions are ones that we've discussed before. Water molecules. Let's use a different one. Let's say how about hydrogen fluoride? Got a single bond like that. Remember when we drew the Lewis dot structure for these? That's it. Hydrogen fluoride. Okay. The strength of attraction. We named that yet? We haven't named it yet. Okay. Fluorine has a much stronger attraction for electrons than hydrogen does. So even though this is a covalent bond where they share electrons, they don't share them equally. Right? Some atoms are more equal than others. So we get a shift of electron density toward fluorine over time. So it produces a dipole moment in the direction of fluorine. And that gives the fluorine side a slightly negative charge and the hydrogen side a slightly positive charge. Okay, so when that's for one molecule, right? If you have billions of molecules in a collection, and this would be a gas, then they would orient themselves. If they approached one another like this, they would repel. So they repel until they find another molecule that's oriented properly, like this. Now you have the positive side against the negative side, and you get that dipole-dipole interaction. This one has a dipole, that one has a dipole. Think of magnets. Right? Magnets have a pole, north and south pole. Molecules sometimes have a negative and positive pole. And that's how they orient themselves. So you get a strong attraction here. That's a dipole-dipole interaction. Actually, it's a special kind of dipole interaction called a hydrogen bond. Right? So this is a dipole, but within dipole, you can have H bond, and you need a special set of conditions for the H bond. You need, and that term I was looking for is called electronegativity. Very high electronegativity in an atom is characterizes it as a very strong attractor for electrons. And fluorine is one of them. Oxygen does. Nitrogen does. Sometimes sulfur does have very strong attraction. And those, let's see, are they going to try to steal my thunder again? Fluorine, oxygen, nitrogen. Okay, they're only giving us fluorine, oxygen, nitrogen. So if fluorine is bound to a hydrogen, oxygen has a hydrogen, and what did I say, nitrogen? Yeah, nitrogen has a hydrogen. Then you get this bond is extremely polar. In other words, we get this effect toward the fluorine, toward the oxygen, toward the nitrogen, much stronger than any other dipoles. All you need for a dipole is two atoms bound together. One of them is a stronger attractor for electrons than the other. Then you can get a dipole. So we could get this dipole with I don't know, carbon and oxygen. Right? Oxygen would be more electronegative than carbon. But this is a special case where the hydrogen bond is a dipole-dipole interaction, but it's much, much stronger. That's why water with two such bonds tends to form a dipole like that and like that. Does anybody know what a vector is? It's an arrow pointing in a direction. And in physics, it's often used for forces. If you have a point here and there's somebody pulling on it that direction, we'll say it's pulling in that direction. There's somebody else pulling on it in this direction. Right? So what's the summation of the two? Well, they're generally pulling in this direction. So we can say, all right, the summation of those two vectors is in this direction. So when these two are pulling, this thing's going to move that way. Okay. So when we take these two vectors here, these forces, these dipole moments, and add them, vector add them, we get a dipole moment like that for oxygen. So that's why this side's negative, that side's positive. And it's a very, very strong difference in charge. It's not a complete charge, not a complete negative and a complete positive. It's only partial. But it's stronger than most dipoles. And that's why water is a liquid at room temperature and not a gas. Okay. Hydrogen bonds, London dispersion forces. Dipoles and hydrogen bonds are permanent. They're based upon the structure of the molecule and the atoms that make it up. London dispersion forces are temporary, but we know they exist. All right, so let's see. Make room for London dispersion. Okay. London is the name of the man who proposed this model. And dispersion refers to the temporary displacement of electrons. It can happen in a big atom, like one of the noble gases, like one of the bigger ones, krypton, xenon. Or it can happen in a molecule, a non-polar molecule. So this can happen for non-polar molecules. It can happen for atoms, if they're big enough. So what does the process mean? It means that for this molecule, say it's something like that, the electrons are in constant motion. But occasionally, they tend to bunch at certain locations. So if it's a small molecule, you might get them bunched over here, like that. That would leave this side slightly deficient. Okay, and this happens in microseconds. So how does that affect attractive forces? right? That's what we're really interested in. Well, if this molecule has a neighbor of the same molecule, then this negative is going to push on electrons, push them away from this side. And this side's going to attract them. So what that does is establish a slight positive charge here by repulsion. And attraction on this side will give the electrons someplace to go. Once you establish that, now you get the forces that are attributed to London dispersion, to dispersion of the electrons. Okay? And this happens very quickly, and then it's gone. But we know it exists. How do we know it exists? Example. Nitrogen. Let's use nitrogen as an example. We draw the Lewis structure for nitrogen, we get, right, nitrogen's diatomic, correct? Everybody nod, yeah. It has a triple bond between the two nitrogen atoms. And if we complete the Lewis structure, it needs an octet, right? 2, 4, 6, 8. 2, 4, 6, 8. So there's your nitrogen. Now, is this going to be polar or non-polar? Is there a difference between the two? No. They're the same atom. So they're pulling equally on electrons. They're the same electronegativity, both of them. So this is non-polar. Yeah, it's a non-polar molecule. Well, remember when we said phase changes? If we want to change nitrogen gas into nitrogen liquid, is that possible? Right? Does anybody work in a hospital or near a hospital? Yeah. You see those big tanks outside? Huge tanks. Right? One of them's oxygen and one of them's nitrogen. Hospitals make their own air. They call it medical air. They mix a certain amount of nitrogen, 78% by mass and 21% oxygen, and that's it. And that's what they pump into the rooms. It's pure. They don't have to filter it. They don't have to process it anyway. It's made from the elements. So it's medical gas. Well, they do it by using liquid oxygen and liquid nitrogen. Let's focus on the nitrogen now. How did it get to be liquid? Right? If it's non-polar, and they're right, we can't claim any dipole interactions, right? Because it's non-polar. It doesn't attract with these types of forces. So if we keep cooling it down, if there are no forces attracting the molecules together, and we just keep making it colder and colder, it'll stay gas all the way down to absolute zero. But it doesn't. At minus 195 degrees Celsius, it turns into a liquid. Why? Because of that. We know this is the only explanation that's acceptable for why this becomes a liquid. Because temporarily, short periods of time, this side becomes negative, this side becomes positive, just for a snap of the finger, even less. But it's long enough, and it happens often enough, that you get the attractive forces that allow it to become a liquid, as long as we reduce the kinetic energy of the molecules to a level that will not disrupt these forces because they're so weak. Okay, does that make sense? Okay, it does now. Hope it makes sense on an exam. Okay, there are other possibilities. Right? You can get ions attracting ions. You can get ions attracting through dipoles. That's why when you put sodium chloride solid in water, right, aqueous solution, it goes right into solution, no problem, right? Because water, remember, it's the dipole here. It's got a dipole like that, so it's negative here, positive here. Let's see, let's balance it here. And sodium and chlorine, when they're broken apart, become ions. Right? So you got this positive side over here attracting the negatives, and you got this negative side over here attracting the positives. So that's a dipole ion interaction. Right? Or if you take sodium chloride and melt it, you got to get it really hot. You still got attractions between the sodium and the chloride ions, even in that liquid. That's what keeps it a liquid. You got to get it really, really, really hot to make a gas out of it. And that would be an ion-ion interaction. Okay. Spend enough time on that. The rest of these slides just go into black and white what I've been telling you. Let's see. The greater the polarity of the molecules, the greater the strength of the dipole-dipole interaction. That's a given. Oops. Yeah, there's an example of our, this particular molecule is fluorine and chlorine together. Right? You can do that. And fluorine is more electronegative than chlorine. So the dipole is going to be negative toward fluorine. And there you show, it shows the attractive forces between the positive sides of the molecules and the negative sides. All right. There's our hydrogen bond description, and fluorine, oxygen, nitrogen are typically those atoms that bond with hydrogen and produce this type of dipole interaction. Now, you can have small molecules like water with oxygen and hydrogen. You can have bigger molecules. Right? Suppose we have, let's see. Suppose, let's see. Suppose we have this molecular formula, C2H6O. Okay. There are several molecules, two that I can think of, that have this formula, but they have different structures. Right? One structure is like this: CH3, CH2OH. In organic chemistry, when you write it this way, that bond is between this carbon and that carbon, and the hydrogens are bound to this carbon. Okay, so just that you don't get confused. You can also write it this way: CH3O CH3. It's the same formula, but it's a different molecule. This is the one I drew earlier, the dimethyl ether, and this one is ethanol, the drinking kind. Okay, so look here. You got the possibility for hydrogen bonding right there. But you don't have it here. That oxygen isn't combined with hydrogen at all. In fact, the dipole is this way, and it cancels out. Dimethyl ether is a nonpolar molecule, whereas ethanol is a polar molecule because of this end right here. So how is that going to affect the boiling point? Which one boils at a lower temperature? Which one takes less energy to convert from liquid to gas? Because it doesn't have those forces available to hold it together. Okay, so the boiling point of dimethyl ether is actually less than room temperature. So that's why when you open a can of this stuff, it vaporizes really quick, and you can smell it on the other side of the room in short order. Whereas you open a can of this, and you're not going to smell it until you get ready to drink it. Right? If this is 100%, we call it crystal clear. Right? And it has a tax strap label across the top of the bottle. We used to buy this stuff for work in the laboratory, non-denatured, because the denaturing components would interfere with our testing, our experiments. But we still had to pay the tax, the alcohol tax. But we buy it in big jugs like that. Okay. So that's hydrogen bonding on a localized level. This end over here is nonpolar, but this end is polar. And you can get big molecules with polar ends on one and nonpolar on the other. That's the way soap works. So anybody here make soap or know anybody that makes soap? You saponify a fat, right? You get lard and you combine it with lye, sodium hydroxide. Okay. And what it does is it breaks the bond between the fatty acid and the glycerol molecule and produces a molecule that is actually ionic on one end and nonpolar on the other. So you get this nonpolar end here, and you get this polar end on this side, or ionic end on this side. So if you use it to wash your clothes, then this end dissolves in the oils because the oils are nonpolar. This is nonpolar. Like dissolves like. This end dissolves in the water. So this bridges the gap between water and the oils because they don't mix, right? Water and oil don't mix. So this bridges the gap. It latches onto the oils that are soiling your clothes and you wash it away. Now, other things have been developed over the years. Now we have detergents with non-ionic polar ends. Okay. And they work. The problem with this is if you've got hard water, calcium and magnesium in your water, you get a magnesium here, or a calcium, let's say. You get a calcium there with its 2+ charge, and on this side, you get another soap molecule. And the end result is scum. Right? You get hard water scum if you use soap. Right? So some places, some houses, some cities will soften their water. They'll run it through an ion exchange mechanism and replace that calcium with sodium. Yeah. I used to live in Baton Rouge. The water down there is very soft. Right? It's got sodium in the water, so it makes you feel kind of slick, but it does do a nice job with your hair. It doesn't leave your hair brittle and kinky like hard water will. Okay. And some of the detergents that they use now have ingredients in them that take that effect away somehow. Okay. The extra strength of the hydrogen bond is due to this electronegativity first. That produces a greater difference between the slight positive and slight negative charges. And it's due primarily to the fact that the hydrogen atom is extremely small. So the approach of one or the other molecules can get closer to. We can get, if oxygen is this big and hydrogen is like that, if I draw them to scale, then when you get this big hydrogen here and these other big oxygen here, it can get really close to that molecule. They call that, if this is big enough to cause a problem, they call it steric hindrance. All right. I didn't mention this also. When we draw the Lewis dot structure for water, if we do it like this, like that, we also have some lone pair electrons up there. And that adds to the negative side. So that's what they're trying to show here. Those bulbs with the two little eyeballs in them, those are electrons. So those are lone pair electrons around the oxygen. So what effect do these intermolecular forces have on liquids? Let me see. I think I'm running a little long, aren't I? 50. We should make it. We should make it. Yeah. The vapor pressure of liquids that have these hydrogen bonds are much lower than those of similar liquids where little or no hydrogen bonding occurs. So if we can identify a homologous series, they call it, where you have similarities, but there are significant differences, where we can kind of identify which ones are, we can tease out the significant differences. For water, a homologous series would be, let's go back over here, like this, like this. So let's look at family. Oxygen. Oxygen's at the top. So the hydride of oxygen is water. The hydride of sulfur is hydrogen sulfide. The hydride of selenium is hydrogen selenide. Right, so that's what we consider a homologous series. The only difference here is this atom right here. Well, the vapor pressure of these two is relatively high compared to water because these two don't exhibit hydrogen bonding. They're polar, slightly polar, but they're not as polar as this one. And that's what this particular diagram shows. If you look at, they went all the way down to tellurium. Okay. We all know about tellurium, right? We identified zinc as tellurium in some groups last time when we did the experiment. Density. One group actually got zinc. I think it was your group, wasn't it? Yeah. And the rest of you, for some reason, got some strange rare elements. Anyway, if you take the dihydride of, let's continue the series. You find that the boiling point decreases as you go. Tellurium is a big atom. Selenium is a smaller atom, so the hydrogens are getting closer. You can actually get the molecules close to one another. But the attractive forces, actually, I think that tellurium is giving us an indication that the hydrogen telluride is giving us an indication of London dispersion forces because it's a big atom. And you can redistribute electron density around big atoms too. Anyway, the series would take us, tellurium, selenium would be a lower boiling point. Hydrogen sulfide is a lower boiling point. Those are measurable. If we continued the prediction, then we would expect water to be down here. The boiling point would be very, very low. And that's why the Earth's surface would be covered with no water. It'd just be all land. And the water would be in the air, if at all. But in fact, the boiling point of water jumps way up. Right? It goes from -60 for sulfur to plus 100, right? 160-degree change, simply because of hydrogen bonding. Sulfur, selenium, tellurium do not have that option. All right. We talked about the London forces. They're weak, temporary. Sometimes we refer to them as instantaneous. In other words, they happen and they're gone. Don't blink, you'll miss it. They're very significant in large atoms and large molecules. So we can see that in the hydrocarbon series. Right? If we look at methane, and then we go to ethane, and then we go to propane. Right? Everybody knows propane, but this is natural gas. This comes out of those cylinders that you barbecue with, or some people heat their homes with them. Propane. And then butane, if anybody smokes, you got a butane lighter. Right? That's the substance in the lighter. And then you just keep going. Right? This would be, let's see, 12. This one would be 14. I'm going to keep going until I get to octane. All right. The reason I wanted to go to octane was that's in your gas tank. Gasoline. The primary ingredient in gasoline is octane. Well, this series, it's only made of carbon and hydrogen, but the boiling point increases this direction. It gets bigger as the molecule gets bigger because the London dispersion forces are more prominent. The bigger the molecule, the more probable you can have an unequal distribution of electron density around the molecule as it gets bigger. And if we keep going, we get to diesel fuel, which is kind of an oily substance. We go to home heating oil, which is pretty thick. We get to asphalt, which is like C12, 14, 16, right? And it actually turns to a liquid or a solid because of these London dispersion forces. They're all nonpolar molecules, but the size of the molecule matters. Bigger the molecule, the more prominent the London dispersion forces are, and more effective they are. All right. Now we can see the trend in the London dispersion forces in the noble gases. Right? They're all gases, but they have different boiling points. Right? You can condense them, but the bigger the atom, the higher the temperature at which they condense. So there's let's see, yeah, helium minus 269. Let's see if we add 4 to that, would be 273. Yeah, that's right, 4K. And then if we get bigger, then the boiling point increases for neon, increases for argon. The bigger and bigger you get, the more prominent and more effective the London dispersion forces are for those atoms. All right. The strongest of all these are hydrogen bonds. And just to check, intramolecular bonds or intermolecular, which is stronger? Intra. Inside the molecule. Those are the strong ones. They have to be. There's no option. Right? And effectively, what that's saying in 5 lines is, if it was the other way around, the molecules get ripped apart. This is flowery language. The brutal language is molecules get ripped apart. So which one of these has stronger intermolecular forces? That is between the molecules. Right? Any of them polar molecules? Yeah, water's polar. Nitrogen's nonpolar. So the stronger intermolecular forces between is water. And here we're talking about pure substances, right? Just water, nothing else. Oh, there's the example I gave you earlier. Ethanol versus dimethyl ether. Ethanol has a relatively high boiling point because it has hydrogen bonding available, whereas dimethyl ether does not. It's a nonpolar molecule with very low boiling point. Okay, which gas would have would behave more ideally at the same condition of pressure and temperature? All right, what do we need for ideal behavior in a gas? Ideal behavior says that a gas is a gas all the way down to absolute zero. In effect, there are no attractive forces that will hold it together. So you just keep compressing it and cooling it, and your gas goes down until it disappears. There's nothing left at absolute zero. But that's an ideal gas. So what does that mean? It means that the attractive forces are not there. There are no attractive forces in an ideal gas. Right? So, which approaches ideal behavior more closely? The one that has the least attractive forces, right? So if you're looking at the difference between these two molecules, right? We drew nitrogen already. That's definitely nonpolar. The only attractive forces with this one are London dispersion forces. Carbon monoxide, on the other hand, is polar in that direction because oxygen is more polar than carbon. Now, I don't think we gave you the trends in the periodic table, did we? No. The trend is, if I just kind of sketch out the periodic table, the trend in electronegativity is lower left to upper right. Right? So the more electronegative are up here, the least electronegative are down here. So all you have to do is say, all right, which one's to the left of oxygen? Well, carbon's to the left, so it's less electronegative. So that gives you a dipole, and then you have permanent dipole interactions, not temporary London dispersions. This would behave more ideally because the forces are weaker. All right. All right, and there's the short version. I already gave you the long version. All right. Oh, we're down. This must be the last two slides. Okay. Good, we got time. And we get to do a lab today. Concept question. To hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. Okay. What's the temperature of your chest freezer? Anybody remember? No? I'm sorry? Well, that would be the freezing point of water, but you generally want it a little cooler than that because, yeah, about 20. Well, 20 Fahrenheit. So you put these balloons in a chest freezer, they're already blown up, and you put them in the chest freezer. When you retrieve them, you're disappointed to find that the balloons are deflated. Right? First of all, why does that happen? I'm sorry? Right. That explains Charles' law. Volume, temperature is a constant. Right? So they're directly proportional. If we decrease the temperature, we decrease the volume. Right? And that's the explanation, is the kinetic energy of the molecules decreases. They're pushing on the balloon with less force, so the balloon shrinks. Okay, let's see. As they warm up to room temperature, they return to their original size. Okay, that's to be expected. What gas law is demonstrated? Oh, well, I already told you. Charles' law. And what happens to the kinetic energy of the helium during the warming process? It increases. Yeah. Remember, temperature is a measure of average kinetic energy of the molecules. So if you increase the temperature, you're increasing the average kinetic energy of all the molecules. They're not all the same, but the average kinetic energy is. So that would be the last one. All right, let's see. What are we talking about with number 2? This one's gonna need calculation, isn't it? Gas water displacement experiment is set up, and it's determined that 0.812 grams of gas displaces 350 milliliters of water. Okay. The atmospheric pressure is 750 millimeters of mercury. The temperature of the water is 20 degrees. And the partial pressure of water is 18 millimeters of mercury. What's the molar mass of the gas using the ideal gas law? Okay. We haven't talked about this one yet. We have all the laws and the information we need to solve it. We just haven't talked about how to go about it. So let's draw a picture. I think that would be helpful. So we've got, we need a water displacement arrangement here. So I got a tank, and there's water. And then I've got a graduated cylinder here with its mouth down here in the water. Right, that's solid. First, when we start off, we fill this thing up. Right, like Torricelli did with his barometer. Fill it up with water instead of mercury. Hold your hand over it, submerge it, and then leave it there. And what's going to happen is, well, since the pressure difference is so little, the water's going to stay right up here until you do something to displace it. So that's what we're going to do next. We're going to send gas into this here. Coming from this container. So we've got a gas that's being delivered maybe from some reaction, 8.12 grams, 0.812 grams of gas. So our substance is that value, and it displaces water up here. Right? So now this is gas up here, and that's water. Okay. It displaces 350 milliliters of water. Right? The atmospheric pressure is 750 millimeters of mercury. So the pressure bearing down here by the atmosphere is 750 millimeters of mercury. Let's see. Partial pressure of water. All right. This space up here has what in it? It's got the gas. Yeah, sure. It's got the gas. But we bubbled it through water. It picked up water vapor in that gas. So up here, we have 350 milliliters of the gas plus water vapor. Okay. And the temperature is 20 degrees. 20 degrees here, 20 degrees here. We have to assume that it's the same in the water and outside the water. All right. Now, I think that's all the information that we're given, except that if we're going to use the gas law, why would we use the gas law? This gas law. The question is, what's the molar mass? What's the molar mass? What do you need to define the molar mass? Right? I say molecular weight, same thing. Molar mass is mass per unit mole. Mass in 1 mole. So we need to know the number of moles of the gas, and we need to know its mass. We got the mass right here, right? That's 0.812 grams. What we need to do is find the moles. That's where this one comes in. To find the moles. The moles of the gas then would be equal to pressure, volume, or T. All right. Do we have everything we need here? Well, let's see. What we have is the volume. The volume is gas and water. But if we take the water vapor out of it, what's going to happen to the volume? If we take the water vapor out of it, the volume should decrease. But we don't know that. What we do know is the pressure, right? Atmospheric pressure on this surface and on the gas inside is 750 millimeters of mercury. What's the partial pressure of the gas? That's what we want to know. We don't want to know the total pressure because we don't care about the water vapor. We only care about the gas. So that's where we're told that the vapor pressure of the water is 18 millimeters of mercury. Okay. So which law are we going to use here? Dalton's law of partial pressures. That total pressure is due to the pressure of the gas plus the pressure of the water vapor. Well, we know the pressure of the water vapor is 18. Now the pressure of the gas added to that is 750 millimeters of mercury. So the pressure of the gas is 750 minus 18. Right? Let's see, 2, 3, 7, right? Millimeters of mercury. Well, we have another problem because this R is what? 0.082, I use 0.06, liter atmospheres per mole K. We need pressure in atmospheres, not millimeters of mercury. So how do we get atmospheres from millimeters of mercury? You don't remember? You need a conversion factor. 760 millimeters of mercury is 1 atmosphere. So you divide 760 into 732, and you get the atmospheres that we can use in our equation. So let's go 732 divided by 760 is 0.963. Yeah, 0.963 is pressure. So this is in the denominator. Pressure is going to be 0.963 atmospheres. And the volume. Well, if we decrease the pressure, then we can use the same volume. We don't have to let the volume shrink because now we know what the pressure is in that volume. So we can still use 350 milliliters. No, we can't. Because this right here, liters. So how many liters is 350 milliliters? Well, if you do it enough, you can do it in your head. But if we use dimensional analysis, 350 milliliters, convert it to liters. Right? What's the relationship between milliliters and liters? There are 1,000 milliliters in a liter, correct? So if we divide this by 1,000 or move the decimal 3 places to the left, we get 0.350 liters. Okay. How about temperature? We need Kelvin, don't we? But we've got 20 degrees Celsius. So how do we get Kelvin out of that? 273. 293 K, right? Now we can solve it for moles. I got 0.963 in here already. 0.35 times that, 0.08206 divided into it, and 293 divided into that. So I get the number of moles is 1.402 times 10 to the minus 2 moles. Now we can put that up here. 1.402 times 10 to the minus 2 moles, and divide that into 0.812. And I get 57.9 grams per mole. Okay. Did I lose anybody? You're probably right. Oh, it's worked out. Let's see if I did it right. Okay. Got mass, volume, pressure, temperature, pressure of water, that's given. Okay. So we're going to get the atmospheric pressure conversion. Actually, we got 732 millimeters of mercury. Then we convert it to atmospheres. All right, then we solve for moles, plug in all our numbers. Yep. I used an extra decimal on my 1.402. All right. Here it is. Rounded off 58. Okay. I think that's the last one.